Hello everyone, I'm Professor Harrison and welcome back to our module on statistical inference. Today we're going to be covering confidence intervals for proportions, what they are, how the formula is constructed, and when the normal approximation is valid. We're following Bess, an investigative journalist on a cold case she can't let go, and today she's investigating a credit rating agency that published a historical default rate without a confidence interval, allowing a number with real uncertainty around it to be used in credit models as though it were a known constant. A major credit rating agency published its annual default rate for a specific bond category as 4%, which was based on 600 bonds tracked over the year. That number ended up in credit risk models across the industry. It got plugged in as a fixed input with no range and no uncertainty. Bez's question: what does the confidence interval around that figure actually look like? To figure this out, she pulls up her case file. Everything we've covered so far for confidence intervals has been about estimating the population mean. But a lot of questions in finance are about proportions. For example, we might ask questions like, what fraction of bonds in a given rating category defaulted within a year? What share of loans go delinquent? What percentage of companies miss their earnings estimates? The parameter here that we're estimating is a proportion, and the formula has to shift to match the fact that we're estimating a proportion instead of a mean. The sample proportion is defined as p hat equals the count of outcomes that meet the certain condition, divided by n, the total number of observations. So for example, if 24 out of 600 bonds default, then p hat is 24 over 600, which is 0.04 or 4%. The confidence interval for a proportion has the same structure as the one that we built for the mean. Sample estimate plus or minus a critical value times the standard error. The one thing that changes is where the standard error comes from. For a proportion, the standard error is the square root of p hat times 1 minus p hat divided by n. Let me explain where that standard error formula comes from, because it's not exactly arbitrary. It follows directly from what we covered in the probability modules. A default or no default outcome is a Bernoulli random variable. It takes the value 1 with probability p and 0 with probability 1 minus p. The variance of a Bernoulli variable is p times 1 minus p. The sample proportion p hat is basically the sample mean of n independent Bernoulli trials. And from the sampling distributions video, the variance of the sample mean ends up being the variance of the underlying variable divided by n. So the variance of p hat ends up being p times 1 minus p over n. The standard error, the square root of that, is the square root of p hat times 1 minus p hat over n. So really, we've derived this in the same way that we did for the mean. The only difference is that we're using a Bernoulli random variable instead of a continuous one, which makes the formula look a little bit different. There is one condition to check before using this formula. The confidence interval for a proportion uses the normal distribution as its critical value source, z alpha over 2, not t. That is valid because the central limit theorem applies here too. The sample proportion is approximately normal for large enough samples. But large enough has a specific condition. N times p hat must be at least 5, and n times 1 minus p hat must also be at least 5. Those two conditions ensure that you have enough successes and enough failures in your sample for the normal approximation to take hold. When those conditions fail, the sampling distribution of p hat ends up being skewed, especially when p is close to 0 or 1. With only 2 or 3 defaults in a sample, the distribution of p hat is highly right skewed. The normal-based interval would understate the uncertainty in the upper tail. This matters in finance specifically because rare events like defaults, operational losses, and fund liquidations are exactly where the condition most often fails. And they are also where the model inputs matter the most for capital adequacy and loss estimation. Getting the interval wrong in those cases ends up being consequential. If you have 300 loans and only 2 delinquencies, n times p hat is 2, well below 5, and the normal interval is not valid. You would need a different approach entirely. Let's check Bess's case. Here n equals 600 and p hat equals 0.04. N times p hat is 24, which is well above the rule of 5. N times 1 minus p hat is 576. So the good news is that both conditions hold. Now let's build the interval. The standard error is the square root of 0.04 times 0.96 divided by 600. 0.04 times 0.96 is 0.0384 divided by 600 gives us 0.000064, and the square root of that is approximately 0.008 or 0.8%. The 95% confidence interval, 4%, plus or minus our critical value 1.96 times 0.8% gives us an interval from approximately 2.4% up to 5.6%. The agency published 4% as their number. However, the 95% confidence interval for the true default rate runs from 2.4% up to 5.6%. The upper end of that range is 40% above the published figure. A credit risk model that plugs in 4% as a fixed input is pricing in less default risk than the data actually support at the upper end of the plausible range. So, any credit risk model might actually be severely underestimating how bad things could go if the true proportion is in the upper end of that range. And it is worth noting that 600 bonds is a reasonably large sample for this kind of analysis. Many agencies report default statistics for subcategories with far fewer observations. At n equals 200, the standard error would roughly double, and the interval would widen to something like 1.5% up to 6.5%. The uncertainty gets larger, not smaller, as the rating category becomes more specific. One more practical note is that the formula we've covered produces a symmetric interval. We go the same distance above and below p hat. Because of this, for p hat values close to 0 or 1, that can sometimes produce a lower bound or upper bound that is below 0 or above 1, neither of which is a valid probability. When p hat is close to the boundary and n is small, you would need a modified interval to handle that correctly. For the range of default rates in most fixed income credit work, where p hat is between roughly 1% and 20%, and n is in the hundreds, the standard formula is the right starting point, and the boundary issue rarely comes up. But the interval still needs to be reported, and a model that treats the sample proportion as a known constant is carrying uncertainty that it hasn't acknowledged. In her article, Bess explains this to her readers. A default rate without a confidence interval is not a fact. It's a point estimate. The 95% interval around 4% runs from 2.4% up to 5.6%, and any model that treats those as the same kind of thing is carrying unacknowledged risk. After filing the column on the agency, Bess pulls up a different table from a case she's been trying to solve. She's been tracking a company called Callaway Value Partners, which at one point was a heavy hitter in the world of hedge funds, but over the last 5 years has had almost all of their money slowly drained from them. She's been trying to figure out exactly why. She's been tracking a figure where she figured out that in 14 of the last 20 quarters, where Callaway Value Partners recorded their largest losses, a fund called TRQ appeared as a counterparty on the other side of the trade. She wants to find out if it's just a coincidence that this party shows up on the other end so often when everything goes bad for Callaway Partners. So she runs an interval. Here, the proportion of trades where TRQ was on the other end of the trade is p hat equals 0.7. The standard error is going to be the square root of 0.7 times 0.3 divided by 20, which ends up being around 0.1, and the 95% confidence interval runs from approximately 0.5 up to 0.9. The base rate for any single counterparty appearing in a specific firm's largest losing quarters in a market which has many active participants is well below 50%. The lower bound of her interval sits right at that threshold. But with n equals 20, the interval spans almost 40 percentage points. It's too wide to support a publishable claim, so she closes her file, wondering exactly what happened between Callaway Partners and TRQ. So that's the confidence interval for a proportion that follows the same structure as the mean. Center on the sample estimate, spread by a critical value times the standard error. The standard error for a proportion is the square root of p hat times 1 minus p hat over n, which comes directly from the variance of a Bernoulli variable. The normal approximation is valid when you have at least 5 successes and 5 failures in the sample. And as Bess's case showed, treating a sample proportion as a known constant, skipping the interval entirely, can materially understate the range of possible outcomes in a credit model.